Alright, in this video I'm going to be going over a vector rotation algorithm, which is just rotating a vector to the left a certain amount of elements. So if you rotate A, B, C, D, E, F, G to the left 3 times, you would get D, E, F, G, A, B, C. So it's a very simple algorithm, but there's a surprising number of ways to do it incorrectly. And so what we'd like out of this code is for it to run fast and use a small amount of space, depending on your specific domain. That may or may not be necessary. And also we would like the code to be readable and maintainable. So first I'd like you to pause the video and try to come up with your own solution to this simple problem, and then see how it compares against the 5 that I'm going to present here. Alright, so coming back from a pause, here is solution number 1. So we observe that rotating a vector to the left n elements is the same thing as swapping the first n elements with the remaining elements. So we are going to use temporary storage, of course, to hold the first n elements, and this runs in linear time using a linear amount of space, and it's very, very simple. So we have our generic function here, and we have an array of elements and a length. That's the number of elements in the array, and n is the number of the size of the rotation, the number of elements to rotate. So first we allocate our temporary storage of n elements, and then we copy from elms n elements into temp, and then we copy from elms plus n the remaining elements into elms itself, and then of course copy back from our temp. Okay, moving on, here is solution number 2. We observe that rotating a vector left n elements is like rotating the vector left 1 element n times. That's pretty obvious. So it also runs in linear time, but there's a larger constant factor. It runs in constant space, and it's also very simple. So here we go. For I from 0 to n, which is the number of rotations, rotate left. And we'll define rotate left here. We grab our leftmost element. We move from the first element all the way to the last onto the 0th element and on, and then we replace the last element with our stored temporary variable. Okay, number 3. The idea behind this algorithm is writing elements to their final location one at a time. So, each element is moving to the left n times, and they only move once, so we know the final destination for each element ahead of time. And so say we want to rotate A, B, C, D, E, F, G left 3 times. We're first going to copy the first element into a temporary variable and write the nth element, so 3, the third element in this case, to its final location. Alright. Then we are going to write the 2nth element onto its final location. So we can see that after writing the third element to index 0, we can then safely replace the element at this index with the element that is n past it. And we proceed in this way using a modulo of the length, of course, when we're calculating our next index. And so say we come to this final point, and we then at this point are going to be reading from the 0th element. We simply use our temporary variable instead and then stop. The cycle has completed. So again, we have transmuted A, B, C, D, E, F, G into D, E, F, G, A, B, C. So if not all of the elements have been written to after the cycle has completed, we repeat, but beginning at index 1 instead of index 0. And this happens when the rotation is a factor, or the length is a multiple of the rotation. So for example, if we're rotating A, B, C, D left 2 times, then we store the first element and we write the second element to the 0th index, and then we write to the second element from the, well, we add 2 and then modulo the length, and we see that that's equal to the 0th element, so then we instead write the temp. So at this point we have CBAD, but we have noted, we presumably have some sort of counter that lets us know that, hey, we've stopped, but we've written only 2 elements and there are 4 in the list. So we repeat that entire process beginning at element 1 instead of 0. And we write to the first index from the third index. And then, using similar reasoning as above, we write to the third index from the temp variable. And then we're done. So this also runs in linear time, and it runs in constant space, but as you can probably glean, it's very, very complicated for something that should be so simple. And unsurprisingly, the code itself is going to be complicated. So first we have our integer that keeps track of the number of elements we've moved, and this needs to be equal to n before we know we're done with the algorithm. So starting at 0 and proceeding until our counter is equal to len. I'm sorry, I might have said n earlier, but we proceed until we've moved every element, so all of them. And then we store the ith element in a temporary variable, and we keep track of 2 different pointers, so to speak, our to and our from. Our to is initialized to I, and our from is the nth element past I. And then while from is not equal to I, so while we know we are reading from elements in the array and not our temp variable, replace index 2 with index from, and every time we do this we have to record that we have moved 1 element. Replace 2 with from, and then add n to from, and then of course modulo the length. And after this while loop is completed, then we know we're attempting to read from the 0th element, so we still have an element to write to, and that is in temp, and we do have to increment our counter here as well. And that is the entire, oops, ignore that. That is the entire algorithm. So you can see that it's pretty complicated, much more complicated than the first and second solutions. Okay, moving on to solution number 4. So we consider some vector AB, where A is a range of elements, and so is B, whose rotation is BA. So this is using the same observation that, you know, rotating a vector is the same thing as swapping at some boundary. So assume that B is longer than A, and then B can be broken into B1 and B2, where the length of B2 is exactly the length of A. So here's our vector A and B. A might be ABC, and B might be DEFG. And we split, we mentally split B into B1 and B2, and then all we have to do is, the vector can be reversed as follows. Okay, so we swap B2 with A. Now A is in the correct location, and all that remains is to swap B1 and B2, which is equivalent to the original problem. So it's you know, we have to rotate by the length of B to the left, or just do a swap. So this is going to be a recursive solution, and it runs in linear time and in a linear amount of space, and it is, I said, somewhat complicated. So we'll take a look here. So our simplest case is when the size of our rotation is exactly half of the length of the vector, and in which case we're just going to swap the elements. So this is the simplest case here. In the next case, when our n is less than our len minus n, so this is the only case I went over in this text file here. We're assuming that b is longer than a. It's very similar logic for the reverse case. But in this case, what we want to do is swap, let's see, this is, yes, we're swapping at locations elms, and also elms plus len minus n, len elms. So here I have replaced the swapped b's with lowercase b's, but of course they were originally from b's. So at this point our a's are in the correct location, and all we have to do is make a tail recursive call to rot with the same elms, but now we've decreased the size of our problem by n. And we're still rotating by the same number, which is n. And so at that point, then we'll have bb, lowercase bbb, which is the correct array. Okay, and then there is a similar block for if the amount you're rotating is larger than half of the array. Okay, so I would say of these four solutions, none of them are particularly compelling. These last two in particular are pretty complicated, but we're about to have an aha moment here. So now consider the same vector AB with rotation BA just like before. We have some reversing function that can reverse a vector at specific indices, or a specific range of an array. So let A prime be the reverse of vector A, and then B prime is the reverse of vector B. So BA can be computed as follows. First we reverse A in place, then we reverse B in place, and then we reverse A reverse B reverse in place, which is BA. So this runs in linear time just like the others. It runs in constant space, and it's very, very simple. So pretty much the best of all three criteria. So here's what it looks like. We're going to use a reverse from the algorithm package or whatever. So if we're reversing well, pretend that says ABC 1, 2, 3, 4. So we reverse that to CBA 1, 2, 3, 4. I'm sorry, reverse the first n elements. Then we reverse the remaining elements from the nth offset all the way to the end. So we have CBA 4, 3, 2, 1. And finally we reverse the entire array, and we have the solution, which is 1, 2, 3, 4 ABC. And if it wasn't clear, here, let me fix this now. So we're rotating ABC 1, 2, 3, 4 by 3. Alright, so I hope you enjoyed that whirlwind tour of algorithms to solve this simple problem. Thanks so much for watching. I'll see you next time.